All right, ladies and gentlemen, happy Thursday. I hope everybody's doing well and that you guys were able to enjoy as best you could spring break. Um, Today we're back. I'm back. We're going to hit on our next topic, which is dynamics. And we just talked about kinematics. This group of slides is all about dynamics. So with kinematics, we were very focused on the motion of an object, but we didn't include any forces. With dynamics, we're still going to be considering the motion of an object, but this time we are going to be looking at the forces and how that affects the motion of an object. So let's launch into this. Before we can get too far in, though, we need to make sure we understand what a system is and what an object is. They're pretty fundamental. I had you guys watch this video, this link by Bozeman Science. I'm going to go ahead and do my best to kind of just summarize some of the main points. But let's see what we can figure out. So an object is a collection of matter or mass, where the internal structure it isn't significant. We don't care about it. A system is a collection of two or more objects. Could be two, three, four. It just depends. So um, object, collection of matter, where we don't care about the internal structure. A system is a collection of multiple objects. So take a look at the picture to the left, this book right here. Would this book be a system or is it an object? Is the book an object or a system? What do you think? Well, the answer is it depends. It depends entirely on what the question is. Um, if a question is concerned with the individual pages of the book, or perhaps even the atoms and molecules that make up the book, then we're going to treat this book like a system. It's a collection of objects, a collection of pages or atoms or molecules. Some questions are going to be more concerned with the book as a whole and where it's moving. In that case, the individual pages don't matter. We don't care about them. They don't affect the overall motion of the book. So we would treat the book as a single object. Hopefully that makes sense. Let's look at an example. A book is at rest on a tabletop. You want to analyze the effect of the forces on the motion of the book, sketch out the different parts you would, or list you could even, that you think would be important to include in this system. So what do you think would be important to include in this system? Write it out, sketch it out, something like that. So in this situation, you're going to want to treat the book as an object, and you'd also want to include the tabletop as an object. As in the previous example, we don't care about the individual pages of the book. The internal structure doesn't matter. The internal structure of the tabletop doesn't matter. So we treat the tabletop as an object as well. With the book and the tabletop, that's really the main thing that we need. Some people might argue that you would need to include the earth because the force of gravity is pulling down on the book, and that could be true. It just kind of depends on what we're considering. But you definitely would want to include the book and the tabletop. You're not going to need to include the fan that's on the other side of the room or a door or anything like that, because they have no influence whatsoever on what we're trying to figure out. Let's look at this one. An egg is falling from a nest in a tree. You want to determine the height of the tree. Sketch out the different parts you would think, or list the different parts that you think would be important to include in this system. So, what would we treat as objects, and what objects would we include in our system? What do you think? Pause it if you need to. So in this situation, we definitely would want to treat the egg as an object. We don't care about the internal structure of the egg. It has no bearing on what we're trying to figure out. Our system would probably include the egg and the ground and the tree. So here's another question. What about the nest? It says that the egg fell from a nest that's in the tree. Do you think that we should include the nest as an object in our system? Some people might argue, yes, we should. It's a part of the problem. But I mean, at the end of the day, when we list the tree or sketch out the tree or consider the tree, as long as we know where the nest was located on the tree, we don't really have to include the nest. That the only thing the nest tells us is the original height from which the egg falls. So as long as we know what that is, it's not the nest really has no other bearing on what's going on. So there could be an argument on both cases. Personally, I would probably just make note of the height, and then I wouldn't bother including the nest to try and keep it as simple as possible. Let's do one more. A football is moving upward toward its peak after having been booted by the punter. You want to analyze the motion of the football. Sketch out the different parts you think would be important to include in this system. So, what do you think? What objects would there be? Or what should we consider objects, and what objects would we include in our system? What do you think? So, in this system, you'd include the football and the ground. You don't need to include the person that might be trying to catch the ball. You also do not need to include the player who kicked the ball. That's a mistake a lot of students will make. They'll think, okay, well, the football player kicked the ball. That caused it to start moving. That's true. But if you look at the problem, we're not interested in the moment that the football is being kicked. We're interested afterwards while it's in the air. Once that person is finished kicking it and that ball is in the air, the person who kicked it is no longer affecting it whatsoever. And so in this case, we would not include the player who kicked the ball. If the question was instead, you want to analyze the forces and motion of the football as it's being kicked, then we would want to include the player who kicked it because there's a force being exerted on it right then. But after the ball has started traveling through the air, that doesn't matter anymore. And so we won't worry about including the player who kicked the ball. So, what is a force? We've kind of used that word a few times. Simply put, a force is any kind of a push or pull that is experienced by an object. You could also describe it as any kind of interaction between two or more objects, where that interaction is pushing or pulling the objects involved. Anytime there is a force, and we'll come back to this later, anytime there is a force, there are at least two objects involved. You do need to remember that. Sometimes students end up creating, to be honest, fictitious forces because they think there should be a force there, but if they would just stop and think about it, well, what are the two objects involved with that force? They can only list one, which would suggest that maybe there's not a force there, and they ended up making something up that didn't really exist. So, well, what do you think? Is force a scalar or a vector? Do you remember what scalars and vectors are? I hope so. If not, look it up. But is force a scalar or a vector? With forces, we care very much about the direction that the force is going. And so we would consider force a vector. It is a vector. We care about the direction that it's going. All right, let's go over some common types of forces that that are a little more common to see. We'll start with the force of gravity. So this is the pull of one object on another object due to the mass of both those objects. Its direction will always be down. Gravity is always, 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 always acting on objects. If an object has mass and there's another object that has mass, there is a force of gravity. All right. Now, if you were to get extremely large distances out in the middle of space, nothing for trillions and trillions and trillions and trillions of miles, or excuse me, we're not supposed to use miles, kilometers, whatnot, then you might be able to, or trillion, better yet, trillions and trillions of light years, you might be able to argue that the force of gravity doesn't really exist at that point. But really, for all other situations that we're going to consider, force of gravity is going to be there. It's an attractive force. The objects pull on each other, and it's always considered down. So let's go over the normal force. The normal force is a supporting force. It's what we would call a contact force. It has to be in contact with another object. The force of gravity not a contact force. No contact necessary. It would be a distance force. All right, it acts at a distance. Normal force has to be contact. All right, so when an object is being supported by the surface of another object, that supporting force is what we would typically classify as the normal force. All right, its direction. Whoa, that's a typo. That says is. I'll have to fix that. Um, so its direction will always be perpendicular to the surface that the supporting object. Okay, so a book at rest on a table. The table is supporting the book, so we go perpendicular or a right angle to the surface of the table. If there's a book at rest on a ramp, the ramp is the supporting surface, and so we would go perpendicular or a right angle to the surface of the ramp. And we'll go over a little bit more about that later. Okay, tension. So tension exists in ropes, strings, chains, other materials like that, particularly when it's taut. It's pulled tight, all right? If the rope or the chain or whatever is loose, then there really doesn't exist any tension in that. It has to be pulled taut or pulled tight, all right? The direction of the tension is always towards the center of the rope. So either end, opposite ends of the rope or the string or whatever, each end is the tension force is pointing towards the center of the rope. It points towards the other end of the rope. You could even think of it that way. All right. Tension, contact force. There has to be contact. Friction force. So friction describes the resistance of motion between two objects. It's a contact force. If there's no contact between the objects, then there is no friction. All right. So these, whenever two objects are in contact and they're trying to move, there's a resistance because of the contact between those surfaces, and we call that friction. Friction, the direction of friction is always going to be in the opposite direction of the motion of the object, or sometimes, even if the object's not moving, which we'll talk about later, it's the opposite the direction that of the attempted motion of the object. Okay, if that doesn't make as much sense right now, just hang on. Later in the slides, we'll get to it. All right. Last one. There can be lots of other forces, but this is the last one that we'll talk about right now. Applied force. There's really not a set definition for an applied force. It's just anytime you have a force that's being applied to an object and we can't really identify it as one of the other types, often we'll just classify it as some sort of an applied force, whatever that is, okay? But if we can classify an applied force as one of the other types, we will. So if I'm just pushing a book across a table or a box, I'm pushing a box across a table with my hand, I would call that force just an applied force. However, if there's a rope attached to the box and I'm pulling the rope to pull the box, I'm pulling the box across the table with the rope, I would classify that force as a tension force because tension is the force that exists inside of the rope and it's what's actually working on the box. All right. Net. Let's look at this. So we've got a picture here of somebody casting a net. Think about what the purpose of a net is. People typically use nets to catch things. In this case, with somebody trying to fish, it creates an enclosed space and it gathers together all of the fish into one location. And then they use that, they pull that back to catch the fish. All right. So we're going to talk about something called net force. All right. Sometimes we're only interested in a single force acting on an object. However, most of the time, we will be looking at multiple forces acting on a single object. So to that end, we will be using something called net force. All right. So in this picture, we can see all these fish are being gathered together into one lump, one total amount of fish right here. All right. Net force is very similar. It collects and combines all of the forces. So instead of collecting and combining fish, we're collecting and combining forces, and we're going to get one final resulting force. Common ways that this is denoted is a capital F which represents force. Remember, this arrow simply tells us it's a vector. All right. Sometimes people include it, sometimes people don't. Whether it's included or not, you need to remember that forces are always vectors. And then they have the subscript net, or this fancy little symbol right here is a sigma, Greek letter, capital sigma. It means the sum of, S-U-M, the sum of, or the total amount of. So this would be the sum of the forces. This way is probably the most common way you will see net force written, and it's the way that I tend to use when I'm talking about net force. Keep in mind, the units for force are newtons. The units for force are newtons. They get their own set of units, okay? All right. Okay, we're going to look at some practice problems, a few practice problems with net force, all right? Remember that direction matters, okay? We use positive and negative signs to help us understand direction. When you get to question 5, you're going to need to use SOHCAHTOA to figure it out, all right? So let's go ahead and go to the next one, okay? Here you have these 5 different practice problems. A bunch of different forces are listed with each one. You have a direction up, right, left, down, okay? When you're actually doing the math, positive and negative will help you understand. Remember, we tend to treat up as positive and right as positive. Down is usually negative, left is usually negative, okay? So pause the video if you need to, and go ahead, try to actually calculate what the net force is for each one of these, okay? Number 5 will definitely be the most difficult one. You will need to use SOHCAHTOA. So pause the video and try to figure out what the net force for each one of these is. All right. Hopefully you paused it, got it figured out. Let's see what the answers are, all right? The first one, your net force should have been 45 newtons. Number 2, your net force was negative 10 newtons. Okay. Notice, if I go back, number 1 and number 2 didn't have up, down, right, left. It was just positive or negative. So we don't include in our answer up, down, right, left. We just have positive or negative. 3, 4, we definitely had right, left. Okay. Number 3, your net force is 10 newtons to the left. 10 newtons to the left. Okay. Simply putting negative 10 newtons here wouldn't work because that could be either to the left or it could be down. You have to somehow indicate the horizontal direction. So if you wanted to say negative 10 in the horizontal direction, that could work. But just negative 10 by itself won't work in this situation. So it's easier to just say 10 newtons to the left. Number 4, our net force is 0. If something has a net force of 0 newtons, that means that there is no force, no net force there, which means that there's no direction. If there is no size to your net force, there's no direction to your net force either. So we did not need to include any kind of net direction, or any direction here for our net force because there's no size to it. It doesn't exist, so to speak, okay? Now, number 5. You could have said you should have gotten 50 newtons, but you also have to indicate a direction. You could have set 37 degrees above the horizontal, or depending on how you set it up, you could have gotten 53 degrees right of the vertical. I'm going to go into how to solve number 5. All right, so just bear tight. If you didn't get that one or you got it wrong, we'll go through it together. So forces that run parallel to each other can be combined just by adding and subtracting, okay? Forces that are perpendicular, we have to do something else. So let's start by looking at parallel forces because those are easy to combine, okay? So up and down are parallel, right and left are parallel. So I looked at the up-down direction and I combined all of those to get 30 newtons. Positive 30 newtons means that it's 30 newtons up. Now I looked at the right-left direction and I got 40 newtons. Positive 40 newtons means that it's going to the right. Okay, positive 40 newtons means it's going to the right. All right. So right now I have a net force in the vertical direction of positive 30 newtons. And then I have a net force in the horizontal direction of 40 newtons, positive 40 newtons, okay? So, oh, well, I just said that. There you go, okay? So 30 newtons is positive. That means it's up, positive y direction. 40 newtons positive. That means it's in the positive x direction. It's going to the right, all right? Now, in order to get a total net force, we're going to have to combine our net force in the x direction with the net force in the right direction. Because they're perpendicular, we have to use SOHCAHTOA and Pythagorean's theorem, all right? So, when you want to combine vectors that are perpendicular to each other, let's start with that. You got to use SOHCAHTOA, all right? When you use SOHCAHTOA, a lot of times it's helpful to kind of sketch out what the vectors look like. So here is what I did. I decided to do 40 newtons to the right. That's my first vector. And then I pick up my second vector where my first vector ended, and it goes 30 newtons up, okay? This dotted line would be my resultant vector. That's my total net force, all right? And it starts at the beginning of the first vector and goes to the end of the last vector, all right? Okay, so the third vector is our net force. We're going to figure out direction. Now, we're going to use this. Now remember, SOHCAHTOA, sine equals the opposite side divided by the hypotenuse. Cosine equals the adjacent side divided by the hypotenuse. And tangent of our angle equals the opposite side divided by the adjacent side. Tangent is going to be most useful right here. So we have tangent of theta equals opposite side 30 newtons divided by our adjacent side, which is 40 newtons, okay? Now, if you do an inverse tangent right here and an inverse tangent on here, because you have to do the same thing to both sides, you'll get an angle of 37 degrees, okay? Now, you could have set this up differently. I forgot that I can do this. You could have done, this is not going to be a straight line because I am horrible at this. You're 40 newtons up, okay? Let me actually, and you also could have done, holy cow, that's embarrassing. That's not 40 newtons, okay? Instead of doing 40 newtons first, we could have first done our 30 newtons up, and then we could have done our 40 newtons to the right next, okay? In which case, our angle would have been right here, all right? Now, if you did this, then you would have had tangent theta of 40 newtons over 30 newtons, all right? And if you recall, I believe it was 53 degrees was the other answer, okay? So you could have done it that way and gotten an answer of 53 degrees. So in this situation, I wouldn't just say 37 degrees. You'll notice I said 37 degrees above the horizontal. So that means I start at my horizontal and I go up 37 degrees. If you did it this way and you got 53 degrees, then what you would say is it's to the right of your vertical, because I went vertical first and then I go right 53 degrees, okay? Either way, all that gets you is the direction. You still need to figure out what the size of the force is. You got to use Pythagorean's theorem. In case you've forgotten, Pythagorean's theorem is a squared plus b squared equals c squared, all right? So you have 30 newtons as perhaps your a squared, 40 newtons as your b squared, or excuse me, 30 would be your a, you have to square it. 40 could be your b, square it. And then your result would be c squared. So do 30 squared plus 40 squared, then take a square root of that. If you do that, you'll get 50 newtons. So your final answer, 50 newtons at 37 degrees above the vertical, or 50 newtons, above the horizontal, or 50 newtons to the right of the vertical, 53 degrees to the right of the vertical. All right? Okay. So let's move on. Okay. Let's talk about force diagrams, or sometimes called free body diagrams. I go back and forth between how I call them, but they mean the same thing, okay? Basically, you're just going to look at a single object. Every force diagram or free body diagram only looks at a single object. If you want to look at the forces acting on multiple objects, you need multiple force diagrams, okay? But a force diagram looks at all the forces acting on a single object, and it gives a very simple representation of those forces and their directions. All right. We tend to represent the object with a box or a dot. I like to use a box. And then we start by drawing forces away from the box. All right. The length of the arrow also helps us to understand the size or magnitude of the force. We also then will want to label the force. All right. Sometimes we'll label it with a number. Sometimes we'll label it just as force 1, force 2, force of gravity, friction force. It just depends on what the problem is that we're looking at and what it's asking us to do. Okay. So let's look at that number 5 example, and let's do a force diagram for it. Okay. So here's our setup. We've got all these different forces acting on a single object. All right. So we're going to start by representing whatever our object is, and then we're going to draw the appropriate arrows in the appropriate directions, and then we'll label them. Okay. So I split it up. You could have done this. I started with just the up down. Okay, with the vertical direction. Notice that you could have done this one of two ways. You could have just gone force 1, force 3, force 4. Force 1 is in the up direction. Force 3 is in the up direction. Force 4 is in the down direction. All right. Or if you wanted to, you could have just not done the F3, F1, F2. You could have just put the actual size of the forces. Notice the length of my arrows. All right. The longest arrow is the 45 degrees. The middle arrow is the 20 newton. Excuse me, not 45 degrees. Wow. 45 newtons. The middle arrow is the 20 newtons. And the smallest arrow is the 5 newtons. Okay. Don't forget the rules for constructing a force diagram. Arrows always point away from the object. Okay. So we've got a box right here that represents our object. All my arrows are pointing away. Always, always, always. Arrows must be touching or connected to the box or the dot. So if you look here, everything's connected. All right. And then arrows that are labeled the same have to be treated as if they have the same magnitude. So if I had just said F, 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 F for force, F for force, F for force, I would have to assume that all three of these forces are the same. But by putting a little subscript 1, 3, 4, that tells me that these are different forces of different sizes. All right, so keep that in mind. Let's look at our horizontal forces, okay? Force 2, 30 newtons right. Force 5, 10 newtons right, okay? So I've labeled it like this. I followed all the rules. Everything is connected to the box. All arrows are pointing away. They are sized, okay? Now, sometimes a problem might have dotted lines and a grid to help you measure out exactly what it should be. For the most part, if you're sketching out a force diagram, a free body diagram, as long as they are approximately the correct size, that's usually sufficient. If I wanted to be technically correct, then this 30 Newton arrows would have been 3 times larger than my 10 Newton arrows. But I'll be honest with you, I didn't care that much. And the problem's not specific in that, so we're okay. Now, the final force diagram would look like this, okay? The other two were just examples of the vertical direction, the horizontal direction. This is what an actual force diagram would look like. It would include all of the forces and their appropriate directions. All the rules are being followed. Things are labeled correctly. Arrows are of varying lengths. They're all pointing away from the box. They're all connected to the box. So these are good force diagrams, all right? We'll skip this slide because I don't have something for you to do right now. I did put a few examples in here. Let's go ahead and see what we can figure out. I'll read these out, then you can pause the video and see if you can construct force diagrams for them. So, construct a free body diagram for a penny that has dropped from rest from the top of a tall building. Then construct a free body diagram for a tire of a car that's accelerating forward at a constant rate. So in this case, we're not treating the car as an object. We're treating the tire as an object. The car would be a system, a collection of objects, okay? I want you to focus on one tire, okay? One tire that's helping to accelerate the car forwards. Think about how, this one's a little tricky. Think about how a tire moves and what it's actually doing with the ground, okay? So go ahead and pause the video, see if you can come up with some force diagrams, and then I'll show you the answers. All right, here's some answers. So take a look at the penny that we dropped. Okay, once you let go of the penny, there's nothing else acting on the object. I said assume free fall. We'll talk about what that means later. I put it just in case you remembered, but free fall means that we're not including air resistance. All right, so the only thing acting on the penny as it falls is the force of gravity. Now let's think about the car. All right, keep in mind it was accelerating to the left. Whoops. There we go. Keep in mind it was accelerating to the left. That was important to realize. All right, so let's say we've got the tire of a car. All right, and if the car's moving to the left, that means it's rotating. The tire is rotating this way. All right, so think about what the tire is doing. At the point where it's in contact, pretend that was more accurately drawn and the tire's actually on the ground. You know what? That's bothering me. Let's see if we can fix that. Better. So the point that the tire is actually in contact with the ground, this point right here, the tire is rotating this way, which means that the tire at this point is trying to move to the right. So the tire, in this case, is accelerating. Where it's in contact with the ground, it is accelerating to the right. Friction always opposes that attempted motion, that attempted acceleration. So the friction force is then going to the right, and that friction force is what pushes the car forward, okay? Normal force is going up because our surface is flat, and then the force of gravity is always, always, always down, okay? All right. So now we're going to go into Newton's laws of motion. These are fundamental. You have to know these, all right? So let's see if you can remember what they are. What's Newton's first law of motion? What's Newton's second law of motion? What's Newton's third law of motion? If you can't remember, pause the video, look it up. All right. Here you go. Objects at rest, stay at rest. Objects in motion, stay at motion in a straight line. Second law, F equals ma. Third law, equal and opposite reactions. So I'll talk a little bit about each one of them. Okay, let's look at Newton's first law of motion. Sometimes this is called the law of inertia. Now, inertia is an inherent property of matter. It helps us understand how much mass an object has and how difficult it is to change the motion of an object. All right, whatever objects are doing, whatever their motion is, the objects try to keep maintaining that motion, and it's the mass that makes that happen, the inertia that makes that happen. Okay, so if an object is moving, its inertia, its mass, means that it's going to try to keep moving in a straight line at the same velocity, same speed, same direction. All right, and it'll do that forever and ever and ever. An object that is not moving, its inertia, its mass is going to try to keep it stationary. It doesn't want to start moving. It's going to try to stay in that state. All right. So objects that move, they're going to keep moving. Same direction, same speed. Objects that are not moving, they'll stay stationary. Both of those are conditional upon the net force being zero. If your net force is not zero, then this does not work. All right. If your net force is zero, then this is what will happen every time. Okay. Newton's second law. All right. So the graphic that I showed, I like it because it has all three of them on there, but a lot of times for my regular physics, I just do F equals ma. For you guys, you need to do the net force is equal to mass times acceleration, okay? You're always going to be looking at the net force equals mass times acceleration. If there's only one force, then this becomes simplified to F equals ma, but always start with the net force equals mass times acceleration, all right? So something to keep in mind is that when an object is only being accelerated because of the force of gravity, so if the force of gravity is the only thing causing the acceleration of the object, then instead of just having a general acceleration, we will call that the acceleration due to gravity. All right, that's our 9.8 meters per second squared. You can round that to just 10 meters per second, but if the only force acting on it, the only force causing acceleration is the force of gravity, then Newton's second law becomes this equation right here. All right. This is what we call the force of gravity. I like to call it the weight of an object. The weight of an object. Okay. If you recall when we talked about gravitation, we came up with a different equation for the force. So actually, we're going to talk about. I didn't mention this. That's okay. We'll talk about it later. The force of gravity. This is the weight of an object. We're going to stick with this just for right now. All right. Later on, we'll talk about the force of gravity for large scale, large distances, but we don't need to worry about that right now. Okay. All right. Newton's third law of motion. So Newton's third law helps us to establish that in order for a force to exist, you got to have two objects. The most common way this is said is that for every action, there's an equal and opposite reaction. That makes it sound like that one force happens first and then another force happens in response. It doesn't work like that. Both forces occur at exactly the same time. All right. I like to say it like this. A force is always the interaction of two objects, each object exerting a force on each other equal in size but opposite in direction. So anytime, and I mean anytime you have a force, that force is the result of an interaction between the two objects, and they're both exerting a force on each other. All right. So let's think about that real quick. All right. Let's say that we have the Earth. Okay. And then we have a person on the Earth. You can tell that this is Mr. Claspel. It's me because of the beautiful bow tie right there. But the force of gravity is pulling me down. However, Newton's third law also says that while the Earth is exerting a force and pulling me down, I, at the same exact time, am exerting a force on the Earth, and I am pulling up on the Earth with my own force of gravity. That seems very counterintuitive to a lot of people, but I'm the one that falls to the ground if I jump. The Earth doesn't come up to me. True. The mass of the Earth means that it doesn't really accelerate up towards me. I'm the one that accelerates down. But the force is the same size. You got to make sure you remember the difference between force, mass, and acceleration. All right? All right. Let's look at the next thing. So that's Newton's three laws. All right? Now, if you recall, I had you all watch the trailer to the movie Gravity. You can watch it if you want. I'm not going to play it right now. I'll just describe what you're going to do. You're going to be in a similar situation as Dr. Ryan Stone, the main character, Sandra Bullock's character in the show. You're out working on the International Space Station, and the tether that connects you to the space station broke. You're drifting away. Your radio stopped working. Nobody knows that you are starting to drift away. That's a problem. Okay. You do have a jetpack, but there's only enough fuel for 1 second. That's not going to last long at all. You've still got that broken tether. You've got a hammer and a screwdriver from what you were working on. Okay. We'll say that the jetpack has half the mass you do. The screwdriver and the hammer have the same mass as each other, but they're still relatively small compared to you. The tether is 5 feet long, but you've drifted more than 5 feet away, so that tether will not reach the space station. You're not going to be able to hook anything on it. So my question for you is, how do you get back to the International Space Station? If you don't remember this, that's okay, because you can use Newton's laws of motion to figure out what you can do to get back to the International Space Station. So go ahead, pause the video, think about it, see if you can figure it out. All right, hope you came up with something good. There's no suicide option, no calling it, okay? No taking your helmet off to try and just get it done with. There is a way to get back, and you need to figure it out. So if you just decided to take your helmet off, then pause the video, try again, all right? For everyone else, you need to throw something away from you. This is what I would do. I would maybe angle the jetpack so that I'm pointed towards the International Space Station. And I would use that 1 second. Hopefully, it at least slows me down, even if it doesn't start propelling me forward. If it does propel me forward, even if I'm moving very slowly, Newton's first law of motion says that as long as there's no other force, I'll keep going in a straight line and I'll eventually get to the International Space Station. But let's assume that the jetpack with the one fuel wasn't enough to get you start moving. I would probably take the jetpack off. I would put it so that my back is to the International Space Station, and I would basically throw the jetpack away from me in the exact opposite direction I want to go, because Newton's third law tells us that forces come in pairs. So if I push my jetpack away from the International Space Station, the jetpack automatically pushes me towards the space station. And then I'll start going in a straight line towards the space station, and I'll eventually get there. Okay? Hopefully that makes sense. If not, pause it, think about it, review Newton's third law till it makes sense. Okay? Look stuff up if you need to. All right? Okay. At this point, we started going into how do you solve a force problem? What's the method? So in this YouTube video, it's Flippin' Physics. He has 5 steps to solve any free body diagram. Check it out. This right here is an underscore, just so you know. But watch the video. Hopefully it makes sense. I'm going to try to go through and summarize some of the stuff. It's pretty good. I like it. So if you want to skip the video and just keep going on with this one, that's fine. But I would recommend that you go back at some point and watch this video. So here are your 5 steps. Start by drawing a force diagram. That's your first thing. Anytime you're tackling a force problem, even if the problem doesn't ask you, just sketch out a real quick force diagram, all right? Then, if you have any forces that are at angles going in more than one direction at the same time, break those forces into component parts and then redraw your force diagram. Depending on the situation, sometimes you can skip step 2 and step 3. If all the forces are only going in a single direction, there's no component parts you need to break to figure out, and there's no need to redraw a force diagram at that point, and you can just jump straight to step 4. Just depends on the problem, okay? Once you get to step 4, you're going to use Newton's second law. Figure out what the net force is. Sum of the forces equals mass times acceleration. Pick a single direction, either the x direction or the y direction, and work Newton's second law for that one. Then, depending on the problem, you may need to repeat step 4 and do the same thing in the opposite direction. So if in step 4, you looked at the Newton's second law for the x direction, then in step 5, you might need to look at Newton's second law in the y direction. All right, those are your 5 steps. So that was a review slide. Let's go ahead. Okay, before I launch into how to use these steps, actually, first I'm going to describe the normal force. All right, and then we're going to apply it. Okay, so The normal force, one of the reasons why it's called the world, wow, that should say word. One of the reasons why the word normal is used is because sometimes in math, the word normal means perpendicular. So when we say the normal force, you can automatically start thinking the perpendicular force. Perpendicular to what? Perpendicular to the surface that's supporting the object. Okay? So, same steps to figure out the normal force. There's no set equation for the normal force. It'd be nice if there was, but there's not. Anytime you need to know the normal force, you're going to have to use Newton's second law to derive. A little scary word, I know. We'll go through an example, but you're going to need to derive what the normal force is every time. Some situations, it's easy. Some situations, a little bit more complicated. I'm pretty sure in the slides that we go through an easy example and a little bit more difficult. So, but take a look through all these steps, same exact steps that we just talked about. All right, so let's look at this. What would the normal force be for a book that is at rest on a table? Well, you've got your steps. Start by drawing a force diagram for the book, then break any forces that you need to into component parts and redo the force diagram. Then set up and solve Newton's second law with the known forces, masses, accelerations in one direction. And then this should say 5, not 4. Repeat step 4 in the opposite direction that you had done. Okay, so let's take a look. So, draw a force diagram. Okay, well, for a book at rest on the table, that's really easy. Okay, force of gravity is always in the down direction, the negative y direction. Okay, now keep in mind our surface. Oh, yeah, I'm really bad at drawing this. I'm not used to being able to draw stuff like this, so I just have to make my best. Okay, pretend that's a table and pretend it's perfectly flat. Okay, if that's our table, that means that the book is resting on the surface of this table, so I need to go perpendicular to the surface, which would be straight up. Okay, so if you look at this force diagram, that's what we have. Normal force going straight up, because straight up in this case is perpendicular to the surface of the table. Okay, no forces are at an angle, so we can skip steps 2 and 3 and go straight to step 4. Set up Newton's second law and then solve for what we need to know. Okay, well, Newton's second law is the sum of the forces, or my net force, equals mass times acceleration. All right. From there, I need to look at my net force. Well, I've got two different forces that are acting in the y direction. I'm looking at the y direction because there are no forces in the x direction. So remember that up tends to be positive. Down, we usually treat negative. Sometimes that changes. We'll go over that in the next example. But positive normal force, negative force of gravity. So that's what we have right here. Positive normal force, negative force of gravity. And those together will equal the mass times the acceleration. All right. Okay. So now that we have this set up, it's important to note something. There's a key word. We've talked about keywords before, okay? The key word here is that the book is at rest. What does at rest mean? At rest means that it's not moving, it's not accelerating, okay? If an object's not moving, it is not accelerating. So we can take Newton's second law and we can set it equal to 0 because our acceleration is 0. Mass times 0 is 0. So we have our normal force minus the force of gravity equals 0. Well, in this case, solving for the normal force is very easy. I just add the force of gravity to this side, add the force of gravity to this side, and you get this as your final answer. So this is the easy thing. If you're looking at a flat horizontal surface, the normal force will equal the force of gravity. Okay. And that's assuming that there are no other forces acting on it. Okay. If you have, let's say it was the book. Okay. Let's say that it's at rest on a table, but somebody has a rope attached to the book and they're pulling up on the rope. Not enough to lift it up, but just a little bit. Well, that's different because now we also have to include tension in here. And so our normal force would end up looking a little different. All right, so keep that in mind. Let's go ahead and tackle a more difficult problem. Okay, so what is the normal force for a book at rest on a ramp that has an angle of theta degrees? All right, same steps. Draw a force diagram, component parts, redo the force diagram, set up Newton's second law in a single direction, then repeat step 4 with Newton's second law again in the opposite direction. All right, so force diagram. All right, now force of gravity is always down, so that's the same. But in this case, the surface that's supporting the book is at an angle. So our normal force still needs to be perpendicular to the surface, which is what we have over here. So in this case, our normal force will be perpendicular to the surface, and in that case, it puts it at an angle. All right, component parts. This one's tricky. All right, we're going to use some of that SOHCAHTOA stuff again. All right, now to make my life easier, I am going to change my coordinate system. Most coordinate systems, all right, most coordinate systems go up and to the right with this being positive x, this being positive y. Okay, most of the time, that's what it is. In this case, I'm going to change it. I'm still going to keep the x and the y perpendicular to each other. But to make my life a little bit easier, I'm going to make the direction my normal force is going my positive y direction. So now my normal force is only in one direction. Okay, I'm going to make down the ramp my positive x direction. So in this situation, let me erase this. In this situation, your force of gravity is going in more than one direction at a time. You could have kept the same thing. You could have kept the same coordinate system and simply looked at the normal force in going more than one direction. I like to keep my normal force in a single direction and split up gravity. Okay, so you can use SOHCAHTOA to break this up into component parts. If you do that, you get the x component divided by the force of gravity equal to the sine of the theta. All right. And then if you solve for that x component, you end up getting this. You can do the same thing for the y component and you get this. All right. I realize that I'm not going into a lot of detail, sketching out how that works and stuff like that. Look stuff up if you need to. Pause the video if you need to. I'll try to see if maybe I can put together another shorter video where I go into that part in a little bit more detail. But for the sake of time, I'm going to try and just move forward. All right. So here are my component parts. The x part of this, keep in mind, x is down the ramp now. The x part is this. The y part is this. All right. So I can redraw my force diagram now. So I've redrawn it with my x component going in this direction and my y component going in this direction. This is going to make it easier to do Newton's second law, which is the next step. I'm going to set it up. All right. The normal force. Right now, I'm only interested in the y direction. So I'm going to start with that. My normal force with my new coordinate system, my normal force is in the positive y direction, and the y component of gravity is in the negative y direction. And that equals mass times acceleration. We're assuming that the book is at rest, which means that there's no acceleration. So in this case, your normal force is simply equal to the y component of gravity. And if you recall, my y component was Fg cosine theta. So the normal force here is the force of gravity times the cosine of whatever the angle of the ramp is. Okay. Once again, if you're not sure how I got all of this stuff, There's some good resources out there that can help you figure that out. Look up what you can. Maybe just do a Google search about breaking forces into component parts or something like that, breaking vectors into component parts. You'll probably find some good stuff. I'll try to see if I can also make an additional video where I kind of go through that in a little more detail. For right now, as long as you can just accept that what it is, then just make sure you follow the rest of this. Hopefully the rest of it isn't too straightforward. I did a substitution. I took my y component and replaced it with the force of gravity multiplied by the cosine of theta. All right. All right. Let's talk about friction. So, it doesn't matter how smooth the surface is, okay? An object can feel really, really smooth, completely smooth, but it's not completely smooth. Even when you get something like ice, which is close to frictionless, it's not perfect, okay? So a table or a surface, a floor, might look flat and smooth. It might feel flat and smooth. So might like this box right here, but if we look at the microscopic level at these two surfaces, you'll be able to see that the surfaces are not smooth. They actually have little jags. It's jagged. They have bumps and stuff like that. And so if an object tries to move, all of these indentations and surfaces are bumping into each other. That's what friction is. Friction helps us understand the resistance to motion because of this very situation. All right. So there are two types of friction. There is static friction and kinetic friction. Static tends to mean that it remains the same. It's unchanging. So when we talk about static friction, we're talking about friction that keeps an object from changing its position. It keeps the object at rest. Kinetic friction, the word kinetic means motion. So when we talk about kinetic friction, we're looking at the friction that exists between two objects when there is actual movement involved. All right? So whether we're talking about kinetic or static friction, there is something called the coefficient of friction. We use this. It's called mu. All right, like Mew from Pokemon. Come on, it's not spelled the same. It's spelled M-U. That's how you spell mu, at least the Greek letter mu. Okay, so mu is dimensionless, has no units. It's scalar, direction doesn't matter, and it's just a property of the material. It describes that force of friction between the two bodies. It helps us understand that ratio so that we can get a feel for how intense the friction of the object is going to be. All right. So here is your equation. Okay, this is the equation for static friction. This is the equation for kinetic friction. You take the coefficient of friction, whether it's the static coefficient or the kinetic coefficient, you take the coefficient of friction and you multiply it by the normal force. Okay, coefficient of friction, multiply it by the normal force. That will tell you what your force of friction is. Okay, now every object will have a static coefficient of friction and a kinetic coefficient of friction. Which one do you use? Depends on the situation. If the object's at rest and it's in a static situation where it's not going to move, then we're probably going to be interested in our static coefficient of friction. We're going to be interested in our static friction equation. If the object is moving, we're going to be interested in our kinetic coefficient and our kinetic friction equation. Notice, this is something that's very important. Static friction will always be greater. There we go. Static friction will always be greater than kinetic friction for a single object. Okay, remember, single object can have a coefficient of static friction, coefficient of kinetic friction. Okay, so likewise, the coefficient of static friction for one object is always going to be greater than the coefficient of kinetic friction. Common sense will help us understand this. If you think about it, it's always more difficult to start an object moving than it is to keep it moving. Okay? If there's a big heavy box and you have to push it across the floor, let me erase that. As in our previous example. Oops. Right there. Okay. So let's say that we have this box and we're going to try to start it moving. It is always harder to start the box moving. It's always harder to get it going than it is to keep it moving. Once it's moving, it wants to keep moving. It's going to try to keep moving. And so it's not as difficult. But when it's not moving, when it's stationary, it wants to stay at rest. So you have to really work against that inertia. Once it's moving, you're not trying to overcome the inertia anymore. You're just trying to overcome the kinetic friction. Okay. So that's this concept right here helps us to get an understanding of that. Okay. It's always harder to start an object. Static friction is always larger than the kinetic friction. All right. So on your equation sheet for my AP students, this is what the equation looks like. All right. I want to mention a couple things. First off, absolute value signs. The direction of friction is always opposite the direction of motion. Okay. Which means that it depends. What it is in an exact situation will depend. There might be times where you have to assign your friction as a positive number, and there might be times where you have to assign it as a negative number, and it will depend entirely upon the problem. So the absolute value signs help us to remember that this friction force is not always going to be in the same direction. It could depend on the situation. All right. Less than or equal to. All right. The actual size of the friction force sometimes depends on the other forces. For example, static friction is the friction, if you recall, that keeps an object at rest. It stops it from moving. All right. So let's think about the box. Let's say that for this box, if you push with 50 newtons, the box will start moving. At that point, you've overcome static friction, and now the box is able to start moving. So 49 newtons, the box isn't moving. Static friction is still keeping it in place, but 50 newtons, the box is now moving. Okay. What happens if I start pushing the box to the right with a force of 20 newtons? Is my static friction going to still be 50 newtons? Well, keep in mind, I'm trying to move the box to the right, so my static friction is going to the left. If my static friction is 50 newtons, then that means that I'll have a net force of 30 newtons to the left, which would mean that I push the box to the right and it starts moving to the left. That makes no sense whatsoever. So what happens is the static friction will actually match what I'm doing. Because I haven't gone over that 50, it will just match. Okay? So 20 newtons. So I'm pushing with 20 newtons. That's not enough to overcome the static friction. And so the static friction will be less than the 50. It will meet the 50, just enough to give a net force of 0 so that the box doesn't move anywhere. Okay? Whoops. Come on. Oh, man. Okay. So I'm stuck on this eraser mode. That's great. Anyhow, that's all right. There's other ways to do this. So that's why this says less than or equal to, is because the friction force will typically match what the other forces are doing up to a certain point. Once it exceeds that threshold, it maxes out. But There you go. Hopefully that makes sense. So let's look at this example. A block of mass m is accelerating across a rough surface by a force F that's being exerted at an angle to the horizontal as shown. Coefficient of friction is mu. What is the acceleration of the box? Okay, well, same 5 steps. Force diagram. Here's what your force diagram should look like. All right, here's what your force diagram should look like. Maybe see, I kind of jumped into that. Maybe pause and see if you can figure out the answer to this question, I guess. I already gave you the free body diagram, so there you go. But why don't you go ahead and pause the video, see if you can figure out what the acceleration of the block is, and then go ahead and resume playing. And I'll kind of walk you through how to do that. All right, so force diagram. Perpendicular surface, or excuse me, flat horizontal surface. So our normal force is going to be straight up. All right. This object is going to try and accelerate to the right. All right. It might try to go up a little bit, but that's usually doesn't happen quite so much. So its motion is likely, at least while it's in contact with the surface, its motion is going to be to the right, which means that the friction force will be to the left. Gravity always goes down, and our applied force is to the right and up. It's going in 2 directions. So you're going to need to break that up into component parts. So here is how you would break your applied force into component parts. Since I have 3 forces that are all going with my normal coordinate system, I chose to leave it the same. I know for one of the other examples, we rotated it, we changed it so that it made our life a little easier. But in this case, if I change it, I'd have to break my normal force, the friction force, and the force of gravity into component parts. And that's just way more complicated. So I'm going to leave my coordinate system alone. And I only chose to break up my applied force into component parts. Here's what it looks like. Okay. Now I redraw my force diagram. So I got rid of the applied force and I'm only putting the component parts. Okay. So this is what your redrawn force diagram should look like. All right. These 3 forces are exactly the same. I just now have the X part of my applied force and the Y part of my applied force. All right. Now, step 4, set up Newton's second law, solve for what you need to solve. Okay. Now, remember, the problem wants us to figure out the acceleration of the box. And since we're assuming that the box is not moving off the ground, that means that the acceleration is going to be completely horizontal. Because I'm assuming that there's going to be some motion, that means I'm going to use kinetic energy to determine what I need to know to determine what the acceleration is. And in order to use kinetic energy, I'm going to need to know the normal force. So I'm going to start with my vertical direction, all right, my y direction, and I'm going to solve for what the normal force is, okay? So here's my setup. This is my net force. I've got a positive normal force because it's going up, positive y component of my applied force going up, and then negative force of gravity going down. And since I'm assuming there's no motion up or down, I set that equal to 0. All right. Now I can solve for the normal force, which looks like this. All right. But I don't like having just this component. I like to use the variables that they gave me. So I'm going to do a substitution. All right. I'm going to take my y component and substitute this value in for my y component, which is what I did right here. Okay. So now I know what my normal force is. All right. So I can go on to step 5 and start looking at the x direction because that's where my motion, my acceleration is going to be. Okay. So Newton's second law, net force. All right. Sum of the forces. The x component of the acceleration is going to the right. So that's positive. My kinetic friction is going to the left. So that's negative. And it equals mass times acceleration. In this case, I'm assuming that I can't assume that there's no acceleration. For the y direction, I could assume that because there was no motion up or down. But because this object's going to be moving, most likely to the right, and I don't know if that's a constant velocity or not. I have to assume that there's probably an acceleration. Plus, the problem asks us to solve the acceleration. All right. So I divide both sides by mass to get acceleration isolated. All right. And now what I'm going to do is I'm going to substitute values in. Okay. So instead of my x component, I'm going to substitute in what that part actually is. And then if you recall what the normal or what the equation is for kinetic friction is, I just did a substitution in right there to figure this out. Okay. However, I'm not done quite yet because I solved for what my normal force actually is. All right. And I substitute my normal force in for that equation. I'll go back. Okay. So here's this. This is my normal force. Everything else stayed the same. All I'm going to do in this next step is I'm taking my normal force and I'm substituting into my normal force. This is my normal force that I solved for. Okay. So this would be my final answer. Bit complicated, but as long as we understand the process, the steps, then we'll be okay. All right. Practice. 2-kilogram book is moving with a constant velocity on a table. Consider friction and round gravity. What is the coefficient of kinetic friction for the book if it's experiencing an applied force of 10 newtons? All right. I'm not going to walk you through this one, and I'm not going to tell you what the answer is right now. I want you to work it, and I want you to see what you can come up with. All right. If you have questions about it, you can email me. You can talk to me about that, and I'll help you out. I'll help you see. I want to see your process. I'm not going to just tell you the answer for this one because I want to see your process so that we can correct any mistakes. And then later on, if you want to know what the actual answer is, I'll tell you. Okay. Let's do another practice one. A book with mass m is moving with a constant velocity v on a horizontal table. Consider friction. What is the coefficient of friction for the book if it is experiencing an applied force of F sub A? And you can assume that that horizontal or that applied force is completely horizontal. All right. You can assume that that applied force is completely horizontal. Yeah. So, and let's say that that is horizontal to the right. We'll say that that's horizontal to the right. So once again, I'm not going to tell you what the answer is. I'm not going to walk you through it. You try to figure it out. If you got questions, let me know. And then I'll want to see your process before I give you any answers for it. Okay. All right. Let's talk about pulleys. Pulleys are very important. It's a device that rotates right here when a string's wrapped around it, and it allows you to change the direction of forces. All right, so gravity's going down here, and this allows us to pull block A horizontally, even though block B is moving vertically. So there's tension. This is a single rope, single string, or whatever. And the tension on either side of the pulley will be the same as long as the pulley and the rope are massless and frictionless, and as long as the rope doesn't stretch or break. As long as these conditions are met right here, then the tension will be the same on both sides of the pulley. All right, so here's a practice problem. All right, we're going to use the same steps to solve this practice problem. Okay, block A has a mass of m sub A. Block B has a mass of m sub B. Neglect the friction in this system, all of it, no friction. And you can also assume that the pulley and the rope are massless. What is the acceleration of block A? Your final answer can only have these following variables. That's it. So I want you to pause the video, use those 5 steps, see what answer you can come up with. Here's my hint. B and A are different objects, so there are different force diagrams. Be careful how you set those up. All right, so pause the video, see what you can come up with, and when you're ready, go ahead and resume playing. All right, let's start with step 1. All right, we're not going to treat the rope and the pulley as an object. So we only have two objects, so two force diagrams. This is the force diagram for mass A. This is the force diagram for mass B. Okay, gravity's pulling down. Notice that I am using, instead of F sub G, I'm using mg, the weight of an object. This is acceptable. Do not just put G. And do not just put M. Those are wrong. M by itself is a mass. It's not a force and has no place in a force diagram. G by itself, lowercase g, is an acceleration. It is not a force by itself. It's an acceleration, not a force, and has no place in a force diagram. Mass times g, mass times acceleration, that is a force. And so it is allowed to be in a force diagram. Keep that in mind. I've seen a lot of students make a mistake like that, okay? So block B, gravity's pulling down, tension's pulling up, all right? Block A, gravity's pulling down, normal force is going up, and tension is going to the right. I have labeled the force of tension the same. If you remember our conditions, we said that the tension on either side of the pulley will be the same as long as those certain conditions are met, which they are. So I will label these tension forces the same because they are the same tension. It's the same size, okay? Their directions are different, but the size is exactly the same. Notice that when I did mg, I am labeling these different. The acceleration from gravity is the same for both, but this one has mass A and this one has mass B. If I just did mg, then I would assume that mass A is the same as mass B, which is not correct. So you have to be careful about that, all right? So no forces are at angles, so we can skip step 2 and step 3. We'll go to step 4, all right? Now block A is only going to accelerate in the x direction, and the only horizontal in the force on block A is tension, all right? So if you recall from our force diagram, tension is the only force acting in the x direction. However, we're not allowed to have tension in our final answer, so we need to figure out how to get rid of tension. What we need to figure out what it equals so that we can do a substitution. To do that, I'm going to have to look at block B. So here is Newton's second law for block B. All right. Keep in mind, we didn't adjust our coordinate system, so down is negative. All right. So our tension force is going up, so that's positive. The force of gravity is going down, so that's negative. And the overall net acceleration is going to be down, so it needs to be negative as well. Okay, because there's acceleration here, I can't make this 0, but I can't leave it positive because it's accelerating down, and that's negative. Solve for your tension force. This is what you get. All right. Now, let's go to block A and do Newton's second law for the x direction for block A. This is Newton's second law for block A, all right? Tension force is to the right, so it's positive, and the acceleration of block A will be to the right, which is positive. I'm not allowed to have tension, so I'm going to substitute in. Remember, I solved for tension right here, so I'm going to substitute this in, and I get this, all right? Now here, I can't stop here because I need to get the acceleration by itself. So I'm going to get the acceleration. I'm going to move this acceleration over to the other side. I'll add MBA, then I'll add MBA over here. So I've got both terms that have acceleration on one side and then everything else on the other side, all right? I do that because now I can factor out my acceleration. When I factor out my acceleration, now I can divide this side by mass A plus mass B, and then I divide this side by mass A plus mass B, and I get my final answer. Okay. Hopefully that makes sense. If not, go back over it again so make sure you can follow it. All right. So the method that we just used is effective. Those 5 steps will always work. However, sometimes it's actually the harder route to go. All right. Sometimes we can actually do something to simplify and It's an easier method, okay? This link right here, I know it's a lot to type, so if you just go to my slides that I post, you can click on the link and it'll automatically bring it up, has a video of somebody going through the easy way. All right, I'm going to go through the easy way as well, but I recommend that you still watch the video. They also have an example in a different one of going through the hard way, but go through it. Hopefully it makes sense, okay? So, easy way. We treated mass A and mass B as two separate objects. Excuse me, the hard way, we treated mass A and mass B as two separate objects. The easy way, we're going to treat all of this as a single object. Instead, we treated it as a system with two objects, but now we're going to treat it as a single object. Okay? We will only consider forces that interact with other objects. Since the tension in here is an internal thing, it's not interacting with other objects because this is now all one object, we don't need to worry about the tension. All right? We're only interested in forces that would interact with other objects. All right? Okay, forces that go in the acceleration, the direction of our acceleration, we're going to treat as positive, and forces that go in the opposite direction of the acceleration will be treated as negative. So, since we only have one object and we only have one force to consider, all right, the only force that causes this object to accelerate is the force of gravity on mass B. So let's set up Newton's second law. I guess to be fair, we could still, I can't really draw it out right now. I don't know what happened to that. We can, you could still draw a force diagram. I was going to draw it by hand, but something's up with the system and I haven't figured out. I don't know how this works yet, so I don't know how to get it back. But anyhow, so I'm going to go ahead and sketch a force diagram, see what it would look like. In that one, you would only have one force going down, and it would be the force of gravity acting on mass B. So when I set up Newton's second law, it ends up looking like this. Keep in mind, so this is my net force right here. Since there's only one force, this is all it is. This, instead of having it equal to MA, my object, my new object is the combined mass. So instead of just one mass, it's going to be the combined mass. So this right here is your M. F equals MA. And then you can divide both sides by the total mass, and you get the same answer that we arrived at. But this was much faster. Okay? Go through it again if it didn't make sense. And even if you're a little shaky, you think you got it or whatever, I still would recommend going through, go back to that link, go through it, listen to the video. They do a good job explaining it. All right, moving on. So what we're going to do now is I'm going to go through and we're going to look at some different stuff like this question right here. I'm not going to go through how to do all this stuff. I've been talking a lot. My voice is going to be very hoarse if I talk too long, okay? But for some of these, I'll give you an answer, but I'm not going to explain it. You need to think about the physics behind it, use these steps, use an easy step if you need to, and see what you can figure out, okay? So in this setup, which is greater, tension 1 or tension 2? Pause the video if you need to. The answer is tension 1. All right, take a look at this situation, okay? Which tension is greater, tension 1 or tension 2? Pause the video if you need to. Tension 2 is greater, all right? So in this one's more complicated. Which tension is greater? Tension 1 right here or tension 2? Keep in mind, this is nice. This graphic happens to break these tensions into component parts for you. So use your knowledge of this to think about it and see what you can come up with, okay? Pause the video if you need to. So the answer to this one technically depends on whether theta 1 or theta 2 is bigger. It looks like theta 1 is bigger than theta 2. If theta 1 is bigger than theta 2, then tension 1 will be greater. However, if theta 2 happens to be bigger, then tension 2 will be bigger. Okay? All right, here's some more practice. We've got a frictionless, massless system set up as shown. What's the acceleration of the block of mass m? We've got 4 choices. Pause the video if you need to. The correct answer is C. New one. A frictionless, massless pulley and rope are set up with 2 blocks as shown. You can neglect the friction on the boxes and the ropes and pulleys, and they're massless and stuff like that. Okay. What is the magnitude of the tension in the string between the blocks? What is the magnitude of the tension in the rope? The correct answer is D. A student pulls a wooden box along a rough horizontal floor at constant speed, which means of force P. Okay, so force P is being pulled on this box right now at this angle. Which of the following is true? That this applied force is greater than friction and your normal force is greater than the weight of the object? Or B, this applied force is greater than friction, but the normal force is equal to your weight? Or C, this force equals this force, and then your normal force is greater than your weight? Or D, this force is equal to this force, and then your normal force is equal to your weight? Pause the video, think about it. The correct answer is A. All right. 2 blocks of mass 1 kilogram and 3 kilograms are connected by a string, which has a tension of 2 newtons. A force acts in the direction shown to the right, assuming that friction is negligible. What is the value of the force? The correct answer is D. For the system shown, assume that mass 2 is greater than mass 1. Assume that mass 1 experiences kinetic friction. Which of the following statements are true? Keep in mind the tension is the tension in the rope. You can assume ideal conditions for the rope, massless, frictionless, for the pulley as well. What will the correct answer be? The correct answer is A. Okay, this one. For the system shown, you can again assume that mass 2 is greater than mass 1. Treat the pulley and rope and everything as massless and frictionless. Okay. You can assume that mass 1 is experiencing static friction. What is the acceleration of block 2? The correct answer is 0 meters per second, or 0 meters per second squared. The frictionless system shown below is accelerated by an applied force of magnitude F. The tension between the strings in the string between the blocks is what? And the correct answer is C. Here's another one. A horizontal uniform board of weight 100 newtons and length 4 meters is supported by vertical chains at each end. Just to be clear, uniform board, that means that the mass is evenly distributed. It's not like one end of the board is heavier than the other. It's evenly distributed. If it had a balancing point, it would be exactly in the center. Okay, so horizontal uniform board, length 4 meters, weight of 100 newtons, is supported by vertical chains, 1 chain at each end, so 2 chains. A person weighing 700 newtons is hanging from the board. The tension in the right chain is 350 newtons. What is the tension in the left chain? The correct answer is C. All right. 2 blocks are connected by a string of negligible mass that passes over massless pulleys that turn with negligible friction as shown in the figure above. Mass 2 is greater than mass 1. The blocks are released from rest. The dots below represent the two blocks, block 1 on the left, block 2 on the right. Draw free body diagrams showing and labeling the forces. Don't do the component parts. There are no component parts. Hint, hint, wink, wink. Draw and label the forces that are exerted on the blocks. Draw the relative lengths of all vectors to reflect the relative magnitude of all the forces, okay? Let's look at some keywords here. Draw the relative lengths, okay? So that they reflect the relative magnitudes. Relative, that means they're not looking for exact precision because we don't know enough information to do that. But we can at least get the general relationships correct, okay? So is the tension force greater than the force of gravity? In which block? Is it less than the force of gravity? In which block? If the tension force is greater than the force of gravity, the arrow needs to be longer. Okay, how do the two forces of gravity compare to each other? If they're the same size, then their arrows should be equal length. If one is greater than the other, it should be longer, that kind of thing. So go ahead, pause the video, sketch it out, and I will show you what this one looks like. All right, I will show you what this one looks like. Okay, here we go. So notice the tension is the same for block 1 and block 2, so those arrows are of equal magnitude. All right? If you recall, we said that mass 2 was greater than mass 1, which means that the force of gravity on mass 2 is greater than the force of gravity on mass 1. This arrow is bigger than this one, okay? In order for block 1 to accelerate up, that means there needs to be a net force going up. So tension needs to be larger than the force of gravity of mass 1. So tension force is longer than this arrow, okay? In order for block 2 to be accelerating down, the tension force needs to be smaller than the force of gravity. Your net force needs to be down. And that's what these arrows reflect. Okay. Derive the magnitude of the acceleration of block 2. So same thing. We're still looking at this situation. All right. I want you to derive an equation that will tell me what the acceleration is of block 2. You are only allowed to have these variables in your answer. Go ahead and pause the video. This is the answer that you should get. Okay. You could use either the short method, the long method. Either way, you should get to this answer. Okay. Now we have a third block added to the system. Okay, so block 3 of mass 3 is added to the system as shown below. There is no friction between block 3 and the table. All right. Indicate whether the magnitude of the acceleration of block 2 is now larger, smaller, or the same as the original 2-block system. Explain how you arrived at your answer. Okay. Notice they don't say you have to derive an equation for this one. You can, and you can use that as your answer. But if you can come up with a good explanation that doesn't involve a derivation, then that's fine. So go ahead and pause it, see what you can come up with. Okay. So first, logic tells us something. Right now, the only thing causing this system to accelerate down, mass 1 up, block 3 right, mass 2 down. The only thing causing it to accelerate really is just the mass of block 2, which means that the force of this mass, the force of gravity on this mass, now has to work not just against mass 1, but it also has to work against the inertia of mass 3. Because of that, we would expect the increase in mass to cause the acceleration to be smaller. If you decided to solve the system. I did it using the easy method. Okay, this is what I got. You'll notice that it looks exactly the same, except that we now have mass 3 in our denominator. Therefore, our denominator will be larger than it was in the two-block system. A larger denominator means a smaller overall acceleration. Okay, all right. Just a few more. So, three forces act on an object. If the object is moving to the right in translational equilibrium, that means straight line. Okay, which of the following must be true? Select two answers. If you want to time it, time yourself 2 minutes. Don't forget to select two answers. Okay, you should have gotten B and C. So this one and this one. Next one, again, 2-minute timer if you want to try to get this fast. A ball is thrown and follows a parabolic path as shown above. Air friction is negligible. Point Q is the highest point on the path. Which of the following best indicates the direction of the net force on the ball at point P? So pause, give yourself 2 minutes. The correct answer is D. Okay, this is the last question. I would say give yourself, I've got a timer here, so if you want to look at the actual slides to figure it out, that's fine. 6 minutes. Try to see if you can get this in 6 minutes. For a system, as shown, assume that mass 2 is greater than mass 1. Assume that everything's frictionless and massless as far as the rope and the pulley go. All right, you can assume that mass 1 experiences friction. What is the acceleration of block 2? You're only allowed to have these variables in your final answer. So go ahead, give yourself 6 minutes, see what you can come up with. Pause the video. All right, here's what your answer should be. You should have gotten an acceleration equal to this right here. All right, ladies and gentlemen, that is all the slides. This is a long one. There were a lot of slides, a lot of content. I tried to have some good examples in there, but it's a long video. So go ahead, watch through the video. Once again, if you have questions or concerns, you don't understand something, just email me, message me, post something in Google Classroom, let me know, and I will help you out as best I can. So, but yeah, go through this as many times as you can. Look for in AP Classroom, look for assignments that be uploaded to help you practice some of the stuff that we've learned. So go ahead and let's end the video. I hope you all have a wonderful day.